Thank you for the introduction, Liz. I'm just going to hold this, it's probably easier. So I'm going to talk about plesiosaurs and more specifically their necks and ask the big question, does size matter? So what I'm going to talk about today is in review, so just bear in mind, no tweeting, and I appreciate that. First of all, why are plesiosaurs interesting? So these extinct marine reptiles with really, really long necks have been reconstructed in various ways previously. And the necks is really the big thing here, like how would they look like, how would they appear in real life? That's the big question, and that's why they're really interesting, because we don't have anything looking like these guys today. Also, the selective pressures driving this even longer neck is something we really don't understand fully yet. And the feeding strategies in these guys is also something that there has been a lot of hypotheses, but we don't really know for sure what they were able to do. So the big question here is really, if you have a plesiosaur that swims forward with a straight neck, what happens? And specifically, if you have a long versus short neck and a thin neck, what happens? And what is really, really annoying in these guys is that soft tissue preservation is rare compared to like ichthyosaurs, and we only have 2 known specimens. So the first one is from Frey et al. Last year. A really, really short-necked plesiosaur or plesiosaur. In this case, you see the dark matter surrounding the whole body. And also Vincent et al. From last year, where I've just focused in here on the neck region. Again, you see this dark matter surrounding the neck. And the big question is then, should we then think more of plesiosaurs, which is the opposite of maybe previously thought, more like sea lions? That's what I've tried to then understand more in this study. And because we're working with marine animals, we have to then just talk slightly about hydrodynamics and more specifically the 2 types of drag there is. And you have, first of all, the pressure drag or the form drag, which is then a function of the frontal surface area. And you have the skin friction drag, which is then dependent on the wetted area of the whole body. And in order to find out this, or try to answer the question, a good way of doing so is by using computational fluid dynamics. So what we did was that we simulated the flow around idealized plesiosaur models. And we used 3 deck lengths and 2 width. So we had to choose some species to base this on, and I'm not going to go into pronounce these names because I'm not really good at that, but what you can see from this is that we have a good range of neck length and also from different families. So a good spectrum here. So to model the plesiosaurs, we needed a base first. We used the initial model for this. We used Victor from Smith and Vincent 2010. So here we just have a 2D image. We need a 3D model. So in order to get that, we use these NURB circles to form the outline of the body. And then you can make a 3D model. Here in frontal view, just to show you. So for the neck length, we then need to increase for the intermediate and the long neck, just to match the neck-body ratios. And for the neck thicknesses, we then had, for the thin neck model, a double of the width of the cervical vertebrae. And for the thick neck one, 3.43 times the width of the cervical vertebrae. Now you might think this is an odd number. It's basically just to illustrate that I looked by eye to just see how, when it would be a clearly thick neck to this guy, and not looking more bizarre than what it should. So that's where it comes from. So the simulations we did here, we used a virtual flow tank. So this cube of 25 meters. And also we had this region refinement in the path of the plesiosaur around it and in the path of it, just to have a better resolution around the model itself. And we had to then have some velocities to test from. So we chose these 5, and it's within the range of estimated swimming speeds of plesiosaurs and above, just to see if something would happen if we go above that. And from the software, I used Autodesk Simulation CFD. And from the software, we can then get the drag force, and then you can calculate manually the drag coefficients. So here are the results, and it's just going to be shown for the 1 meters per second, because you saw more or less the same for most of them in terms of the flow velocity pattern. And here you see the streamlines that follow all 5 models nicely. Not much of a difference. Same here from the top and side view. You can see a little difference in towards the others in the long neck one, where there is a slightly bigger area of low velocity behind the model, but not much of a difference really. Here, the frontal view, and just down in the corner, you can see where we've cut at the base of the neck. So the black circles you see is basically cut through the neck. And you can see from the thin and the thick neck model that you can see a difference. So it's pretty clear here. And just notice around the long neck model again, there is a lower velocity, a lower flow velocity pattern going around the neck. Not much else going on. But what we could see is in terms of pressure, in the thick and thin neck model, and there is a clear difference here you can see in terms of the pressure surrounding the base of the neck for the thin neck model compared to the thick neck model. So here are the results in terms of the drag coefficients, and we can see as expected that the increase in speed would then increase the drag coefficients. And also the neck elongation does not really affect the drag force, and the pressure drag dominates over the friction drag here, so the neck elongation doesn't really alter the frontal area. So for a straight neck model in a plesiosaur, we can see that the thicker necked, model experienced reduced drag compared to the other models. And the broader neck reduced the surface area, normal or near normal, to the flow direction, so we see this reduction in the pressure drag. This could then indicate that we have a hydrodynamic implications that was not really limiting the selective pressures in the evolution of the long necks of plesiosaurs. But we then see that the longer necks probably have a major effect when bent. And this is something I've also looked into. It's probably going to be a talk in the near future, hopefully. So you can look forward to that. Also, ecology and behavior of plesiosaurs. So in terms of if you go above this estimated swimming speed of plesiosaurs, it would probably not be able to then bend its neck because it would basically break off due to the pressure drag. So to conclude, does size matter? For the length, no, but for the width, yes. So there is no disadvantage that we see to have a long neck doing forward swimming. And a thick neck is more hydrodynamically advantageous. And these simulations we have made provide some good support for that we should think of plesiosaurs more like these sea lions, of course in a lot of cases, or most cases, a lot longer. So it's changing the previous thoughts about how we reconstruct these guys. That's all from me. Thank you for listening.